Hi everyone, my name is Enrique Paillas. I'm a postdoctoral fellow at the University of Waterloo. I'm really glad to be participating in this conference, and I'm looking forward to having interesting discussions with all of you. So my talk is going to be about galaxy clustering, which is my main area of research. Today I want to highlight a project that me and my collaborators who are listed here have been working on during the last year. So as you all know, we certainly live in very exciting times to do cosmology. Our cosmological paradigm rests in a model that has been tremendously successful at explaining several key observables in the universe, such as the CMB and the large-scale distribution of galaxies. But despite its remarkable success, there are still a few small details we need to figure out about lambda CDM, namely what is the nature of lambda and what is CDM as well. So in other words, what is the true underlying physics driving the dark sectors of the cosmos? And to add to this cosmological puzzle, even within the lambda CDM framework, we find interesting tensions between measurements from the early and the late time universe, now commonly known as the Hubble and the SI tensions, and this has also now become a research area on its own. This is largely due to the excellent data that surveys such as SDSS, DES, and KITS have provided. Ongoing and future projects such as DESI, HSC, Euclid, or Rubin Observatory will further develop our understanding of these questions and will likely raise some other questions that will be perhaps even more puzzling. So one of the most robust ways to constrain cosmology with large-scale structure is through the so-called power spectrum or two-point correlation function, which measure the excess probability of finding pairs of galaxies separated by a certain scale over a random distribution. Now, these statistics have been widely used in galaxy surveys for several decades now, putting very tight constraints on the growth rate of a structure and the geometry of the universe at different epochs. The power spectrum or the galaxy two-point correlation functions are essentially measures of the galaxy density field in terms of its variance. So they are measuring the variance of the density field as a function of scale. And as such, they provide a complete statistical description when we are dealing with Gaussian density fields. This was the case in the very early universe where the initial conditions, which are thought to be very close to Gaussian, had evolved only moderately. This, of course, also applies to very large scales in the present universe, because these large scales still fall within what we call the linear regime. On the other hand, as the universe evolves, this initially Gaussian density PDF becomes very skewed due to nonlinear gravitational evolution. So the overdense peaks keep growing as the voids empty out, but the voids cannot be emptier than empty. So the density PDF is bound from below at -1, which inevitably skews the density PDF, so it develops significant kurtosis and skewness at very small scales. The consequence of this is that the power spectrum now is no longer a complete description of the galaxy density field at small scales. So we need to look at higher order correlations if we want to capture all the information that is available from this density field. So in this example that I borrowed from Istvan Sapudi, I'm showing two density fields that have the same power spectrum, but different higher order correlations. And the fact that they are strikingly different from each other just by eye is already telling us that the two-point function is not the end of the story in such a case. Of course, extracting this non-Gaussian information from small scales is far from easy. The power spectrum is still perhaps the most robust way of doing precision cosmology with large-scale galaxy clustering nowadays, both in terms of the theoretical development and also when it comes to the understanding of observational systematics, right? However, if we want to make sure that we are really squeezing all the juice out of our $100 million cosmological experiments, we also need to look at alternative clustering methods that can be complemented with the standard two-point measurements, right? This is, in fact, a very active research area nowadays in cosmology, with several new statistics which are being developed actively in DESI, Euclid, and many other ongoing projects. And the idea is to build these new methods to extract information which goes beyond what the standard power spectrum can capture. During the past few years, me and my collaborators have been working on developing a new technique that we call density split clustering. So these methods builds on many ideas that are currently present in literature, such as weak Lansing density split statistics and the separate universe approach and Gaussian self-statistics. And the idea of the method is quite simple. So we want to combine the clustering signal of galaxies which are living in different density environments of the cosmic web. The advantage of these statistics is that they are sensitive to non-Gaussian features of the density field, which allows us to extract information that goes beyond the standard power spectrum. The algorithm can be summarized as follows. So the first step is to smooth the galaxy density field and sample it around randomly placed query positions. And as shown in this figure on the left, this distribution of overdensities can be pretty non-Gaussian. So when we then split these query points into different quintals or overdensity bins, which are demarcated by the different colors on the figure on the right. And these different quintals are probing different environments of the cosmic web. So the first quintal on the left is probing very underdense, void-like environments, whereas the quintals on the right probe high-density regions such as filaments and nodes. So once we have measured the quintals, the next step is to calculate the clustering signal associated with each environment. And we normally look at two different statistics. The first one, exemplified on the left, is the autocorrelation function of the quintal positions, which measures the excess probability of finding a pair of query points belonging to the same quintal, separated by a scale S. We also look at the cross-correlation function between the quintal positions and the entire redshift space galaxy field, which is what's exemplified on the right. And this cross-correlation function is actually the observable that carries most of the cosmological constraining power in our analysis. To motivate the development of this new clustering technique, we began our project by making some Fisher forecasts based on the Quixote suite of simulations. There we found that the density split clustering technique, which is shown by the yellow contours here, provide more precise constraints than the standard two-point correlation function analysis when it comes to the lambda CDM parameters. Which is quite interesting. However, the Fisher forecast can only tell you how much information you can expect to extract from a given observable, assuming that you have a model that correctly captures the cosmological dependence of your data vector, right? But the Fisher forecast doesn't give you the model to actually do that in real data. And actually, the most challenging part of extracting cosmological information with this new technique that we have developed is actually building an accurate model that is able to capture the way in which these statistics depend on cosmology down to very small scales. Because at small scales, the Gaussianity of the density field no longer applies. So it becomes much more challenging to develop, for instance, analytic methods based on perturbation theory to model these observables down to very small scales. So in our work, we have developed a simulation-based model for density split clustering, which is based on the Abacus Summit suite of simulations. Abacus Summit is a state-of-the-art suite of embodied cosmological simulations that were designed to meet and exceed the expectations of the DESI survey. And this suite of simulations includes mocks that were run with the same initial conditions, but different cosmological parameters. So we can measure the density split statistics in each of these simulations with different cosmologies to see how does the observable depend on these different parameters. The caveat with this is that we only have 85 such cosmologies, which is of course not enough if what you want is to build a smooth model of the correlation functions as a function of all these lambda CDM cosmological parameters. So in other words, we would like to know what does the observable look at an arbitrary cosmology that is within the prior range of the parameters that are spanned by the Abacus Summit mocks, right? So we need a way to interpolate in this very high dimensional parameter space between our measurements. And that's where the cosmological emulators come into play. So we have built a neural network that was trained on the Abacus Summit simulations that allows us to make model predictions for any combination of cosmological parameters that are within the prior range of the emulator. So we are taking the Abacus Summit measurements and we are feeding those measurements for all the different cosmologies into this neural network. And the neural network is learning about the dependence of the data vector on all these different lambda CDM parameters. So at the end, it's able to interpolate in this very high dimensional parameter space. So if you ask it, what's the prediction for this given combination of parameters, it will give you an answer based on what the net learned from the training set. Of course, to validate this whole process, you need to validate it in a test set of simulations that was not used for the training process in order not to bias your analysis. So we have validated the emulator against a set of test simulations that we separated from the training sample. And in this figure, the measurements from these test simulations are shown by the colored circles with the error bars. And the solid lines are showing the best fit emulator prediction from an MCMC analysis to this particular simulation. And we find that the model is able to accurately predict the clustering signal down to very small scales for all the different quintals probing all the different density environments, which is exactly what we want. Now in this figure, I'm showing the recovered cosmological constraints from one of our test simulations using 3 different summary statistics. So the green contours show you the constraints on the standard galaxy 2-point function, for which we also built a separate neural network in order to compare. And the red contours are showing the results from density split clustering, which, as you can see, provide tighter constraints than the 2-point function, while they'll still manage to recover the true cosmology of the simulation, which is shown by the dotted line here. And in the blue contours, we show what you get if you combine these 2 probes. So the combination of the galaxy 2-point correlation function and density split clustering, which, as you can see, gives you even more constraining power. So this is highlighting the fact that these 2 probes are also complementary to each other, which is very, very powerful. And during the last few months, we have been working on the application of this density split technique on the SDSS BOSS CMASS galaxy sample. So we have developed a modified version of the code that can handle all this complicated survey geometry from CMASS. At the moment, the constraints are still preliminary, so you should not take these values for granted. You shouldn't take the constraints at face value. But we are hoping to release these new results within the next few months. So please stay tuned for more updates. So I think I will wrap up here and leave you with this summary slide, where you can also find my GitHub repository if you are interested in having a look at the codes we use for our analysis, which are actually all public. And I just want to thank the organizers for putting this together and hope to talk more with all of you very soon. Thanks a lot.